In this video, we're going to talk about some more advanced techniques for solving resistor circuits. The first one we're going to talk about is called mesh analysis, and it turns out it, at a glance, looks kind of similar to our branch current analysis. We're actually going to draw the same circuit we used for the branch current analysis just so the connection is even more apparent. So we have 10 volts, 15 volts, 3 kiloohms, 10 kiloohms, and 5 kiloohms. Okay, so with our branch current analysis, we defined current values through each of these parts of the circuit and used those to make a combination of Kirchhoff's current laws and voltage laws that gave us this system of equations that we could solve. Mesh analysis is basically exclusively using the voltage law, but we're still going to name some currents. So what we're going to do is we are going to, for each little loop that makes up our circuit, we are going to define a current. So these aren't just like voltage law loops anymore. This is actually current I1. To keep this consistent with the other version of this problem that we did using branch current analysis, I'm gonna name this current on the right. Instead of calling it I2, I'm gonna call it I3, and then our equations will end up the same. Okay, so with the mesh analysis, we still do our little walk around around the loop, and it's gonna look pretty similar at first. So starting from the lower left, we have a delta V of plus 10, then we have a delta V of minus 10K times I1, and then things get funny because now we go down and I1 is going through this 3K resistor, but I3 is also going through this 3K resistor. So our voltage drop here depends on, we can kind of think about this as the net current, of including both I1 going down and I3 going up. So I3 is in the opposite direction we're going. So I3 should make this delta V big, or positive, and I1 should make this delta V negative. So you can hopefully convince yourself that this is going to be minus 3K times I1 minus I3. Or in other words, if I3 was 0, if it was just I1, this is just to get the minus sign right. If I3 was 0 and we just had I1, this would be a negative delta V, and that's what we have here, minus 3K I1. I3 is in the opposite direction, so it has another minus sign. Okay, and then going the last bit across the 15 volt, we have minus 15, and that equals 0. The second thing we do is another loop around the right half of the circuit. So starting from here, we get plus 15, and now we have the opposite thing happen. We have minus 3K times I3 minus I1, because we're going in the opposite direction. We're going up through the 3K resistor, not down like we were before. So we're up here, and now we just have minus 5K times I3. And now we're back where we started, so that equals 0. The result of this is that we have a system of equations, 2 equations and 2 unknowns, so now we can solve this. We never had to invoke the current law. All we did was look at these voltage loops, assuming these values of the current circulating around these loops. Why is this useful? Well, honestly, it's a little harder to do this on paper, for me at least, than it is to do branch current analysis. But if you are a computer program solving circuits, this is much, much easier. And the reason for that is before we had 3 equations and 3 unknowns, now we only have 2 equations and 2 unknowns. For large circuits with lots of nodes, this can reduce the number of equations significantly. Like solving linear equations does not scale linearly. So if you can reduce the number of equations by a factor of 1/2, you are speeding up that computation by a lot more than a factor of 2. So that's why mesh analysis is popular. But if you solve these equations, you'll get exactly the same thing you do solving it the way we did last lecture and using branch current analysis. All right, and then if we wanted to find voltages, we could use the current values to find the voltages at different points, using Ohm's law. Okay, the last technique like this is something called nodal analysis, which really is, I don't want to say the opposite, maybe the complement to mesh analysis. So rather than splitting our circuit up into a mesh of these little loops, you identify nodes in your circuit, that is particular points, and use the voltages at those points as the unknown. So instead of a system of equations to solve to get the currents, you end up with a system of equations to solve to get the voltages. Nodal analysis can work with voltage sources or current sources, but if you have something, and we talked about how to convert between them in the previous lecture, if you have something that looks like this in your circuit, a resistor in series with a voltage source connected to something else, you will have to convert this to a current source in parallel with a resistor. And the reason for that is if you try to do it this way, you'll see why. It's because you don't actually know the voltage that's across the resistor. Okay. So let's do an example using voltages. I just made this one up. Okay, so we have a 6-volt source and a 3K resistor, and this is connected in parallel with a 1K resistor. Then over here we have another resistor and another voltage source. You'll see why if we had current sources are very easy to include in nodal analysis, so you'll see why that's what that means in a second. All right, values. This is a 2K resistor. This is a 4K resistor. Okay, so the first thing you do with nodal analysis is you identify the different nodes in your circuit, and nodes really just means places, really means junctions where these wires come and meet together. So since we're thinking about this in terms of voltages, remember any 2 points connected by just a wire have to be at the same voltage because that's what wires do. So looking here, all of these points that I'm circling in red, all of these points are at the same voltage. All of these points are at the same voltage. Different than this voltage, but all of these are at the same voltage among themselves. And then of course, all of these at the bottom are also at the same voltage. So these are the nodes in the circuit. You could also call this a node, but if you're trying to minimize the number of equations, it's easier not to, and as we'll see, convert into a current source. Okay, so our nodes are, I'm just going to name them, we'll call this voltage V1, we'll call this voltage V2, and we will call this voltage V0. Like always with voltages, we have the luxury of shifting it, shifting all of our voltages up or down or by the same amount. And so we can call, we can pick one of the voltages to call whatever we want, or, really what we're doing is picking a point in our circuit to ground. So if we decide to ground V0, that means that we already know the value of V0. V0 is just equal to 0. Okay, so with the nodal analysis, what we do next is we apply Kirchhoff's current law at each of the nodes. Okay, so let's look at node 1, where there's voltage 1 right now. So the current law is that the current going in equals the current coming out. So right away, if we're looking at this over here, we would like to know how much current is entering V1 it's not immediately obvious because we have a voltage source here. So what we can do is we can convert this to a current source, and I'm going to do this by putting a parentheses around this. So we're gonna like ignore that, and then draw in brown over here. This is our current source that we're going to add. We have a current source in parallel with a resistor. Kind of ran out of space there. And this current source, this was our rules for converting before. The resistor is the same as this resistor. So this is a 3K resistor, and the current source is I equals V over R. So this is a 2 milliamp current source. I really wanted it to be in a different color. Hopefully that shows up okay. All right, so now we have something to say about the currents. The currents flowing in to node 1, right? First we have 2 milliamps of current. I guess, the node extends over here now. The current in is 2 milliamps. And, we can, just like other times, you can decide whether or not you want to make the currents going in or out. I'm going to say this current, that current's going in. We're going to say this one's going out, this one's going out, and this one's going out. So 2 milliamps is equal to, so I equals V over R. So we want V, the voltage difference across this resistor, that is V1 minus V0 over R, which is 3K. And of course, V0 equals 0, so we could have plugged that in also if we wanted. All right. We also have current flowing through this 1K resistor. That's going out also. It's going from V1 to V0. So we have another out term that is V1 minus V0. And again, that's 0 over 1K. And lastly, we have this 2K where current is flowing from V1 to V2. So we say plus V1 minus V2 over 2K. So that is one of our equations. We only have 2 unknowns, so we only need one more equation to apply. And it turns out the next one is an easy one, because when we have 2 nodes that are connected by just a voltage source, that gives us an equation relating those voltage sources, right? If this, did I never write down the value of that voltage source? This was supposed to be 10 volts. Apologies. If we have this voltage, the number of this voltage source, 10 volts, then we know that V0 plus 10 equals V2, and V0 equals 0, so V2 just equals 10 volts. So yeah, presumably if things were more complicated, we could have got another equation here and a system of equations to solve like we did in the past, but I wanted to show you what happens when you just have a voltage source connected between 2 nodes. All right, so nodal analysis, also useful. If you're gonna apply these techniques by hand, it's really just whatever you're the most comfortable with. I'm kind of a branch current analysis, or more realistically, blindly applying the voltage law or the current law to like chip away at the problem. That's what I do when I don't really have a plan of attack. It can help to get comfortable with these. Nodal analysis in particular is important because this is basically how SPICE works, the model, simulation software we're using. So you draw your circuit, it identifies these nodes in the circuit, and it, has some set of equations that it solves for the voltage to get your answer for the operating point.